I had taken a look at these in the past um, about thinking of operations as controls, but now that I'm touching Grover's algorithm again, I wanted to take a look at it again because basically one of the implementations of Grover's algorithm is this really neat one here from Craig, and basically you can, if you get basically rid of all the displays, it's a pretty neat and compact version of the algorithm. Really, you've got the oracle, and then you've just got like this kind of operation. That's not a really common operator though, but we'll get into these right now. That's basically what Craig describes in here, which by the way. Um, I just kind of realized that's a bit of the Hadamard sandwiches that Sendex is talking about. So that might be useful for you, Sendex. Take a look at these. Actually, it's pretty. Uh, I think now I understand that because of all the other different things that I've been taking a look at, and I'll try to see if I can, because the goal for the video is, okay. So the goal for the video is basically try to break this down a little bit more and understand, and see if I can get closer to an intuitive explanation of Grover's algorithm that does not touch maths. Um, so Craig mentions in here that this should actually get you close to understanding the rotating towards the solution interpretation of what Grover's algorithm is doing. That's the one that actually I'm not super happy with because of the it's just it's a geometric proof of correctness, and it still goes through the maths of through some kind of maths, and I mean, at the end of the day, that's what it is, right? Rotations. But it's like I feel, first of all, I want to get a bit more convinced about this, and second, maybe there's another way to explain that. But one thing that I've been recently playing with in my head is the fact that, and that's what I want to try today, is the fact that in Xanadus, in a photonic quantum computer, you basically have, um, so you've got like two observables, position and momentum, right? And uh, let's say position is x, right? And then you've got like some sort of distribution function that looks like that, and then you've got your momentum, which is p, and in turn that's going to be something like this, right? So it's kind of where you've got certainty that that your measurement is going to be somewhere here along those like most probable values. Then you've got like you're really uncertain uh, when it comes to momentum, right? That's kind of the trade-off. And actually, I thought about one thing which is, at the end of the day, the blocks here defines three different observables: the z, the x, and the y. And I thought maybe it would be worth taking a look at this implementation of the algorithm and trying to observe what's going on in the x observable and in the z observable. The reason I'm trying to do that is because and it kind of came one idea that came back to my mind was in the very beginning of my channel. I was playing with some of the Kodoku's games. The the one, it was Hello Quantum, I think, and actually there they were basically introducing some of the operations in terms of what happens in between those different observables, which I found it awkward at that point in time, and then I quickly left into something that is more of the traditional way of taking a look at circuits, or other people's way of taking a look at circuits, and not that much these. But from now on, then I keep coming across the idea that, for example, the Hadamard exchanges x and y, and that's really what also Craig mentions here at the very top of the article, right? So right here, somewhere here, I don't remember where. Somewhere in here, he mentions that basically that's it, right? So um, and so I wanted to basically, let's just mishmash a bit of all these ideas into this video and see what happens. Again, my point is to do something like this. So for example, I'm going to be using my touch screen because it's going to be faster for me to build up for, to build up sort of the displays in here, and maybe it's not a bad idea if I just reduce the dimensionality of these. So actually I'm gonna The oracle is just basically a control, like a multi-controlled Z, um, that just, here it chooses a pattern 11011, and that's the one that's flagged. Um, and I'm gonna basically uh, get rid of that and do it like with 3 qubits. I think it's gonna be easier to see. Um, these things, by the way, like this is nothing else than a basically like, so that would be the equivalent of like putting a hard mark here, a control, another hard mark, right, and then doing like so, something like this. So basically you've got this, and and basically a Z, and then so this here is the equivalent. So if this here equals this whole thing here, sort of a sandwich control, it's a Hadamard sandwich control Z, to use Zendex terminology, and I'll try to go through that explanation again in a moment, but that's just so you know. And then the oracle basically is that stuff. So you've seen probably most of Gerber's implementations to actually have like X gates in here, like a bunch of X gates, and then I think at the other side, I think that's what most people see, if I'm not wrong. Could be wrong. Grover's algorithm images. Internet is slow here, but that's basically the only reason these are not in here is because Craig uses a bit of an not that common implementation where instead of starting with a superposition that has all zeros as a seed, like it starts with a superposition where everything is 1. So it's basically here, if you take a look at, if you put like a block sphere, like they're all like minus states, not plus states, all of those. So that's the difference, and it kind of works out if you take a look at how this evolves, and it works out. That makes the whole thing with the notation different, easier, and it also makes a point that you don't have to start with the superposition of plus states. You can start with any. Like the idea of Gerber's algorithm is not. The Gerber's algorithm is more of a finding something that's encoded in a phase operation, or in a phase shift, and then make it putting it into the amplitudes, so you can measure it with a Z observable, and that's the idea. So the essence is that you've got an oracle, and that the fact that you're adding a relative phase for that particular component of your state, it's what you want to then have in your amplitudes at the end of the circuit. That's the point. It's not just a surge. That's sort of a surge is like a more pragmatic, or a more concrete. It's a more concrete goal, I would say, or version of these. That's the more generic. Yeah. No. Wait a second. It's all X's. Oh yeah, and actually Harmar. Okay. Yeah, of course. So that's even worse. I mean, worse in the sense that that's like a control Z. Yeah. Yeah, but it's all a layer of X's here. We'll take. I mean. Yeah. So let me start from. Let me just clear all, and then we'll just we'll just do something similar, but with 3 qubits. So it's gonna be. I hope it's gonna be easier to sort of build the displays in here. Hotmarts. And so basically, the first thing you do is the oracle. I'm not gonna make an oracle function. I'll just go straight forward and say my oracle is 1 0 1. that I might make that oracle maybe. How can I, does this work like that? Column range 2, no, 3, 3, no, all, oracle. Is that it? Yeah. So now I can basically do this, right? So my oracle is this thing. So if I take a look at, if I now basically put the amplitude display in here, I will see that the difference between this display, the difference between this display and this display is exactly the element 101, which is this one here. That's the one that you see the face is changed, right? So that's kind of the whole point of the oracle. Is it controls that. As a controls that, but like so it basically phases the element that it adds a phase of 180 degrees to the part of the Earth's superposition that has that particular pattern. Now the Grober's operator, or the sort of the amplitude amplification operator, that the way that Craig describes it in this case is the following. So it's these, and these. So, and what's happening now here, you can see, is that the amplitude here is growing, and is already, because it's a 3-qubit case, it's already a pretty significant increase. So we don't need to iterate over that much, but if you would do another, and then you would kind of do the same, I think would probably be done by now. So if I do that, it's almost 100%. It's almost 100%, it's like 94%. So we could, you could do even another one, and then you would have exactly that. So, oh no, now, okay, so now you're already past that. Okay, so this is that point where if you do too much iterations of it, then you're kind of going backwards. So we'll stop here. 94% is enough. So now my point is, I want to try to understand, so I want to try to understand a bit what's happening here, right, in between the 2 dimensions. So one way of taking a look at this is basically, how can I do this? So if I wrap a display in a Hadamard sandwich, then that display is telling me what is the X observable of that system at that point in time. Exactly. So this means, like, for example, if we're here, we put this chance display. The chance display, by just in and of itself, it just basically shows you the Z observable, which means it's in an equal superposition, right? And here we're just taking a look at the amplitude, so there's no phase information in this display. If I put another phase, another display in here, but now I surrounded by Hadamards, right? And I surrounded by Hadamards because, sorry, I wanna, the first layer of Hadamards basically is rotating the whole thing, the whole system, so I can take a look at the X observable, and the second is to undo the computation, so I can go ahead with my circuit. So basically, you have to think of this as being one block, and as you can see, it's all 1 1 1, which, if you remember well, like the way we usually talk about the X observable is the plus and the minus, right? So the minus is the one that when you apply a Hadamard gate and it turns into the 1 state of the Z observable, and that turns into the 0. So Quirk is not showing you pluses or minuses. That could be an extension. That could be an interesting extension. Basically, an X observable display, which would basically do that. So, but so you have to imagine, if it says 1 1 1 here, it's the chance of a minus minus minus. I guess so. So can I make a gate out of this? No, I cannot make a gate out of a measure out of a display, right? If I do can nest display, sorry, yeah, pity. Anyway, so we will have to. It's gonna be maybe a bit cumbersome, but maybe I could separate. No. Maybe I know. Maybe I'll make something like just not to, so I don't have to put hardmarks all around it. So I'll make a gate which will be 2. So it's going to be basically this, and I'm going to call this the X observable. So or switch X. So basically what this is going to do is it's gonna do switch X, and basically so when you see that, it means that display is just gonna be showing us the X. So if I put it, okay, so it's gonna make it easier. So we're not gonna see so many hardmarks around. Okay, so basically what I want to say. Okay, exactly. So what we see here is now we are seeing at that step after the hardmarks here applied. This is our Z observable. This is our X observable. And as you can see, it's actually pretty similar to what you would expect, as I mentioned before, between the X, the position and the momentum, right? So one is really, has a spike like at minus, 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 and the other one is like really spread distribution across all the possible values. So that kind of makes sense so far. Now, what happens when we apply the oracle? So now I'll take a look at after we apply the oracle. So we're going to put another change display, another change display. So I'm going to do this. Okay, so now let's bring some clarity here. So here we've got like our superposition. These are our displays. This is the oracle, and these again are displays. The Z and the X. Now that's interesting. So what we see in here is that it seems like part of these certainty has been taken and basically spread across everything else. In the X observable, so in the Z observable, I'm just gonna call it Z and X. Maybe in the Z, nothing has changed from an amplitude or from a probability perspective, but this has changed from, because what this kind of, the way that I see this, the way that I could see this is that what the oracle is doing, right, is what the oracle is at the end of the day, right, as you can see here, is just a control Z, but like with the second control is a turned off control. But really, when you do something like that, the controls are also operations, in the sense that implies that whatever operation you're doing here, it just applies to one particular portion of your superposition. So it actually implies a superposition. So I'm a bit tempted to say that for that particular 101, right, we are carving a portion of that because that basically is a a state where all the probabilities accumulated to this state, minus minus y minus minus minus. So if you apply the oracle, the effect that this could have in the x observable is that it takes a portion of that particular value, because it's just one, right? It's one value out of all the different 8 possible values, and it distributes the I can't, not so sure why this makes sense though, but this seems to be the effect. Takes a portion of it, distributes it. Okay. And then we have this, which basically essentially what it means. I've been thinking about this for a while. Let me get some water. What this basically means is that, so let's take a look at this first of all. Controlled operations partner, for example, the core of gross. Okay, this is the controls are bracketed by Hadamard gains. The bracketing is Blattning-Grover's algorithm. This pattern of control surrounded by H is common enough that it's worth packaging into a single logical thing. I call that an x-axis control. In this post I'll be presenting x-axis controls in diagrams with a little circled plus. The reason I call this H control H thing an x-axis control is that instead of conditioning operations on the control qubit being a 1, axis control conditions operations on the control qubit being a minus. And that state is on the x-axis of the blocks here. So what this is saying is that it's basically telling us that if you could think of it this way, if this qubit is in a minus state and this qubit is in a minus state, then apply an x, apply a naught in this qubit. But here this doesn't help me a lot. It's a bit unintuitive to think about it as controls. The thing is, if I remember well, I think there was another way of looking at it. What if, because I'm thinking just if basically if that opens, yeah, so if I'm in a superposition, right, and I apply a controlled Z, what this does is basically it flips the phase for that particular pattern 1 1, right? If I were to replace that with this, then it would flip the phase for that one, yeah, the basically 1 0, right, and so on. So, and that, pay attention that the controls are operations that also act on the Z observable. It's a control on whether the qubit is a 1 or a 0. So it's a control. It's like if 1 or 0. So this if it really depends on what you're observing in the Z, right? And the effect it has is it has an effect in the phase. If you take a look, if you take a look at the amplitudes from a Z perspective. Now, if I take a look, let me do it not here but here, so it's going to be clear. If I am not in a superposition, right? So all I want to do now is I want to basically, I'm measuring the state 0 0 from an X perspective, right? So I'm again wrapping the display in Hadamards. But I'm still like it's 0 0 the state, right? Now I'm gonna apply a this, and now I'm gonna do another of this. Yeah, that's what I thought. Forget about this for a second. But look at this. So this is a display, this is display, right? Just forget. We imagine you're just applying this operation to the state 0, 0. What this is doing is basically, if you take a look at the system from the X perspective, it's actually flipping the face of the minus minus, or the 1 1 in this case, right? So it acts like a control Z, but on the x-axis, and you can only appreciate that if you measure the x-axis. Now, still, what is going to be the effect of this in the Z? I don't know. Well, here you can see that it's actually that's confusing. It's exactly this. Yeah, 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 yeah. I mean, I don't know, but you get what I mean. My point, right? So, um, but in reality, let's get rid of these for a second. In reality, what's really happening here, remember, is you've got a Hadamard, Hadamard, Hadamard. Then you've got like a control, uh, Z, and then you've got like another Hadamard. It's just that's really what it is. Because if you, what I want to show is, if you now, if now I after this Hadamards. So I'm here and now I apply Hadamards. If now I put displays in here, change displays, put 2 again. The second one will be wrapped in the switch operations. Pay attention that what happened is they flipped, right? So this before was the Z and this was the X, and now exactly this thing here, it's here, which is kind of the first display, which is the Z, and this guy is here, which is in between the switch sandwiches. So this is the X. So they flipped, and that's exactly what the Hadamard gate does, right? It just flips those 2 dimensions. Now, my next question is it worth going from here, or should I stick to Craig's notation? Let's try to do both. Let's try to stay here first. So let's clean that up. So I am now good. I am now here. So I've switched, at that point I've switched the displays, the content, right? So now what would try to let's try to reason what happens. So let's put 2 change displays here, and I mean, okay. So what's weird is we're applying, first of all, we're applying a control Z, and this is still something that I don't know why it must be a control Z. Pay attention that actually one thing that I realize is that here we've got like a 111, right? So and that's awfully similar to what we're doing here. And actually, if you don't have those here, pay attention. As I said, you have like a bunch of X wrapped in here before, so that can be the reason. How do you get to that conclusion? Yet I don't know. But let's think a bit farther. So when you do that, you would expect you're operating on the Z observables, and you're basically saying that um, you want to flip the sign for the component 111. Uh, but I'm assuming if you're flipping the sign here on your Z observable, as we've seen before, what it means for your X observable is that your amplitudes get moved around. If all your, if you're shifting like the phase, if you look at it from the Z perspective and you're changing like on the Z observable and you're changing the phase, right? That is actually, if you take a look at it from the X observable perspective, that phase shift translates into an amplitude shift from that perspective. So if I wrap this around, that's really what's happening. That we've gone from, that's super weird. So we've gone from, this is my previous X and this is my current X. So you've gone from an equal superposition here, and now you've got like a amplitude accumulator here, which is the state we are looking for. But why is it the one we're looking for? That's interesting. We might have to add the amplitude displays here as well in the picture to take a look at what's going on with the phases, because this definitely has to do with interference. But basically that's it, right? I mean, these last Hadamard's are not needed really, because we know how the algorithm. Oh yeah, wait a second. They are needed because now I broke this down into that block, and that block. Remember, that's like one operation. I mean, that's like belongs to the amplitude amplification. So I do need to do do need to add chance display here, another chance display here, wrap it with switch operators. So now, and now they flipped again, of course. And so remember that they flipped again, and actually the only thing this takes you to is like, now this is your Z, and this is something you can now measure, or you can also kind of apply the same operator again, which we won't do because it's gonna get too long. But let's take a look. So why this is where I'm kind of intuitively lost. So I understand the effect of the Hadamard. That's okay. It's flipping those two perspectives, these two observables. But here, let me clean that up. Here's where I'm getting lost. Where am I getting lost? I'm getting lost between so the effect that this control Z has on the X observable. This is what's kind of confusing, because you're going from an equal superposition to this, right? Here, if I take a look at the oracle here and kind of going from these to these, because that's also your X and your X. It's also not straightforward, I think, yet, but it's kind of, I kind of see where this could be going, as in you're taking a portion of your possible states, which is just one, like it's one, out of 8, right? And you're distributing it across the other, because of the oracle, you now have to consider superposition. But it's just that one portion, that one particular thing you're phasing. That's why you don't have an equal superposition here. I don't feel super comfortable with this, but it seems like this could be an intuitive explanation. It's like almost like you're carving out a portion of these and then spreading it out, spreading it across. Okay, let me put some amplifiers. I'll put them in between the sandwich so they also reflect the X perspective. So okay, but that's interesting because basically, let's take a look at this. So we're now taking a look at. Sorry, I forgot one here. So we're taking a look at this X versus this X, right? Because that's the effect the oracle has. Because from the Z perspective, we can understand it, it just flips the face. But what's going on in the X observable, so that face flip translates into the creation of that superposition that it's unbalanced, right? And it's biased towards 111. It's biased towards 111 because that's what your original superposition was starting with. And maybe that's the reason why you're using a 111 here in the first place. That's the point. Let's say. So, but it's still curious to see that the phases are kind of like there is some sort of different phase in here. Oh, there's like a particular phase pattern in here because of the oracle. Mm. Mm. What is the what is the just let me clean that up, and uh, if I do a 101 and I do now like that, is that anyhow similar to is because that's the what's the oracle, right? 101. It's kind of the opposite, really. Almost, because it almost feels like, I mean, the 111, like the minus minus minus, doesn't change the phase. Hmm. What can be the reasoning behind these? Why, if you apply that, um, wait a second, it is similar if to a superposition. Is it the same like? Uh, no, it's not the same. It's not the same. Taking a look at it's kind of no, it's not the same at all. So how does this? So where does this come from? Well, what is the? So that oracle, if I were to apply that oracle to the x, that would be What, like wrapping it? No, 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 that's not. That's not. I was thinking if I wrap it in Harmas, that's not what I'm looking at for. So I certainly don't know where these phases are coming from. Sorry for the mic mess right now. Why the phases in that particular setup, in that particular order? Then you're playing Hadamarts. So I'm assuming those things switch as well when you play the hammer. So I'm not gonna. I mean, I can do this. So basically, these things have flipped, right? So yeah, this one. Sorry, this one is kind of this one, right? And this one is this one. Yeah. And now we're applying the Z. That's where it gets interesting. The Z. So we've got one in here and the other one in here. So what's going on here? After you apply the Z, your Z observable yeah, it's kind of like it's taken these and it's just flipped that phase. That's all it did. That's all it did. Apologies for the sound. I'm not in my usual room, so this is a bit of a mess. And I can't really move around. I'm getting lost with so many displays. Yeah, and then obviously you apply Harmon again, and then those things flip, and that's what you want. But I'm still intrigued then by the effect of this Control Z intuitive effect on the X observable. Because look at it, look at this. What are the similarities? So what is this similar to? They're like opposite. They're like opposite. I don't know. Like opposite to these. I don't know. So I'm kind of lost right now. Maybe I should just try using the Craig's version of the operator, because we know what the Harmards are doing, but then the Control Z effect, it's almost like this is Z. So you're saying take Z, so nothing happens to Z other than this gets flipped. But what happens to X is that they get the amplitudes accumulate around the 101. Why? Why around the 101? That's what's nuts. That effect of this operation into this observable here, which is the X, because that's so what you're saying, and the X before that is this X here. That sort of X as X prima. So here they look like the opposite phases, the opposite phases, the opposite phase, but that phase doesn't change here, and the opposite phases. So it's almost like you would say, because here the effect of the oracle on that X observable was to take a chunk of this and spread it out. But now here we've got, maybe let's try to study that concretely. So we've got an X observable that is in an equal superposition. That is an equal superposition. And so applying that is basically like saying that taking a portion of everything that was 111 and rotating the face. That's gonna be an awfully long video. I'm trying to think, what else could this be? So how could I explain that effect intuitively? Maybe I can't. But this is the Z observable and this is the X observable. This is saying for these flip the phase, which is really what's happening here. But that phase flip translates into an amplitude change, correct? But why exactly that amplitude change? 101. Well, because that's the phase, because that's exactly what the oracle is doing, right? Like, it's what the oracle is doing is phasing those things, phasing that particular element off. phasing it off, phasing it off. Hmm. I don't. That's. I can't find an intuitive explanation for this. You know, if you go and you do the maths, then they probably make sense. But it's like intuitively, how does this even? How can this even get close to any, even to this geometrical explanation? Where was that? That was here. A plane span by. Rotating, 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 blah blah blah. Hmm. 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 I don't understand it. So what's the effect on the x observable? Intuitively, why does it accumulate to 111? It accumulates, sorry, to 101. It accumulates there because you've created a difference in phase, and so what? So what's the effect? Why? What's the effect? Why does this affect X like that? I don't understand. I don't understand. Mm. What have I done? Okay, let's clear it all again. I'll not get that crazy with this place right now again, but I'll try to do one thing. So I'm doing. So now I've got the superposition. Oh crap! I forgot. I lost my. Maybe if I go back and I say clear circuit, exactly now I don't lose the custom gates. So I've got these things. Good. Then I apply my oracle. Right, and then I apply the control. Is that no? The this thing X. Yeah. So another way that Craig tells us to read this is, I think, how to face Hilbert space is of course a very useful tool for intuition when thinking about quantum circuits. For example, the controls-only approach makes Grover algorithms simpler in two ways. First, it pushes you to think in terms of the overlap between the solution vector and the diffusion vector, which leads to the elegant rotating towards solution interpretation of what Grover's algorithm is doing. Second, it makes the circuit a whole lot more compact. So, with let's backtrack and go over some reasons calling it individual wise as this target is useful. Okay, now this is that's fair complaint. Control. Can't. The controls. I hope you stand again. So in the same way that every rotation has an axis, every single qubit operation has a corresponding control. We can freely change which qubit is the target of an operation, which actually, without actually changing that operation, as long as we keep the axis consistent. Yeah. So essentially, that means that would not make a difference. For example, right? No, exactly. So. What this is saying is, if I so how to face the Hilbert space. Is that explained anywhere else? So it's basically to change. Well, every operation defines a control, and every control defines an operation. There is no inherent reason to stick with the conventions of classical computing, where these concepts are unambiguously distinct. For example, from the view of single qubit operations as controls, it's trivial to define what classical computation is. Classical computation is what you get if you can combine z-axis controls with exactly one axis control. What I think this means is that you would basically phase the state for all the minus minus minus. Yeah. Which is really, I think, what's happening, right? So if you take a look at if we put two amplitudes displays in here, and we surround them by, didn't we just do this? Yeah, I think we just did this. Exactly, it faces this one, right? That's correct. Cool, let's get rid of this, because there's too much clutter. But then my question is, so what's the impact of this operation in the z-axis in that case? Because the oracle, basically, let's say it acts on it acts on the z-axis. So we know what the effect is on the z-axis. It's a phase shift, and we know what the effect of this is and the effect of this is. This is also a phase shift, but if you look at it from the x-axis. Interesting. But this means that after that operation here, right? If I take a look at the amplitudes and the chances of the x observable, right? It's done this thing. It's created this spread which I don't fully understand how are those phases and where they're coming from. Intuitively, I think that it means, we're coming from a state that's not in superposition in the X observable, so we just need to take a chunk out of it and spread it all over the place, because now we're basically saying, okay, from an X perspective, right? Um, or from a Z perspective, for this combination, you know, apply a apply a phase rotation. And now the question is, now that this combination, like this means that we're turning that into superposition. It's a mast, right? Because it can be anything, and only that particular example is one we're taking out of that certainty and then spreading it out across everything else. Mm. If and now and now I take a look at that operation, and it's obvious the effect this has on the X observable, but what is the effect this has on the Z observable? Is that it basically, uh, you can think intuitively that a phase shift in the x-axis creates an amplitude shift in the in the z-axis. But why that particular state? That's the one we're trying to find. Why? It's got to do with a combination of these, a combination of these, and a combination of these patterns. That's what my gut feeling is telling me. So that's what my gut feeling is telling me. I'm gonna stop the video here. I have to think a little bit about this, and I'll probably make another video on this. But I have to admit that I found that way of seeing the operations and the controls actually way better than I thought. Because if you open that up and think about the Hadamars, then all you're doing is like you're switching the information in between. But then at that level is much. It at that level seems to be maybe an easier starting point.